Okay, welcome everyone. Simone is going to be telling us about chiralization of star products. Please feel free to start whenever you're ready, Simone.
Okay, so hello everyone, and thank you for inviting me here. So, I'm going to talk about chiralization of star products. So, star products are the main object of study in the formation quantization of Poisson algebras. So, Poisson algebras are the classical limit of associative algebras, and quantization is sort of going the other way around. So we want when star products are this sort of deformation of the commutative product of the Poisson algebra that sort of recovers this, gives this quantization. Now the idea of this work was to try and take this theory that exists for Poisson algebra and see if we can get some sort of equivalence or related stuff in sort of the chiral world, so in the world of vertex algebras. So vertex algebras can be thought as are the chiralization of associative algebras, and we have a chiralization of Poisson algebras, which are Poisson vertex algebras. And these are, again, one, the classical limit of the other. So we have sort of the same framework. And so it made sense to see, look into this and see what happens. So I'll start by a brief overview of the case for the classical case for Poisson algebras. So I'll talk about so this star product for graded Poisson algebras briefly. So as I said, the star product is a new operation, which is called star. This is supposed to be an associative deformation of our original product. So if we have, well, we can call it, sorry, we can write it here as this sort of sum of these operators Cn. These are all bilinear of negative degree. And it's a deformation in the sense that from the first one, we recover our original product. And it's a deformation of also all the Poisson algebra by the fact that with the second one, C1, sorry, I need to move the, because I have my toolbox is overlapped by the Zoom. Well, let's see if it works. Okay, so yeah, sorry. So okay, so it's this deformation. Now, usually when people talk about star products, they also care about the formal deformations. So maybe they'll add here a formal parameter, this, and we'll take this to be an infinite series. Now here, since we with this assumption we made that these things are graded, that all these further terms in the deformation are of increasing negative degree, this will be always a finite sum for the degree reason, and we can get rid of this Tn, maybe putting T equal to 1. So this is a slightly special case. And let's see a couple of examples of star products, famous star products. So the first one is the Moyal-Weil star product. It's probably, well, it's actually the first star product that was studied in depth. This comes from physics. So again, the idea of all these ideas of quantization come from physics, from the fact that when we switched to quantum mechanics, we moved from the commutative world of Poisson algebras to this world of non-commutative algebras. And the idea with this Moyal-Weil star product was, well, what if we still keep using the formalism that we had for the classical physics, so this phase space of this classical phase space, and instead of changing that, we just change the product that we use. So in this way, we can, using this star product with Moyal-Weil star product, one can sort of formulate this quantum mechanics inside the classical phase space. So take the same algebra, take the same space, but change the product. That's sort of the idea. From a mathematical point of view, we start with this 2n-dimensional symplectic vector space, and we take the Poisson algebra that we consider is this the symmetric algebra on it, which of course is a Poisson algebra, bracketing used by this symplectic form. And the formula for the Moyal-Weil star product is the following. So it takes this form. It's a multiplication. So this is just standard multiplication of the exponentiation of this omega half. So omega here, you think of it as the Poisson bivector associated to this symplectic form. So this will be a sort of bidifferential operator. So you exponentiate this and act on A and B. So for example, in the simplest case, say dimension 2, when this space is generated by this x and y, we can write this explicitly, takes this form here. So for example, if we want to compute y star x, this will be, well, we use this formula. So first we do exponentiation. The first term is just identity. So we get sy. Then we need to apply this thing once, and we see that the first term gives 0 and the second term gives -1/2. And then every subsequent application of this always gives 0. So this is what we get. For higher degree terms, you have more terms, of course. Okay. The other example connected to Lie algebra is the good start product. So start here with Lie algebra G, and we take as Poisson algebra the symmetric algebra on G, which again is Poisson algebra with the bracket, the Poisson bracket given by the Lie bracket and then extended by Leibniz. So again, this star product look is a sort of similar form. So we see here. So we have again the exponentiation of this bidifferential operator. This D now comes from the Baker-Kalper-Hausdorff formula. Now, so again, we have our bidifferential operator. Baker-Kalper-Hausdorff formula is this formal series here, which tells us how to compute. Is the formal expression that solves this equation. We can write it in, to get the bidifferential operator from this formula, we write it in terms of the basis. So we get here all the coefficients, and then we just consider this part here. Moving forward, and we change these coefficients here with the differential operator acting on the first and second term. So we end up with something that looks like this: 1/2 of this first sum here, and then so on. 1/12 here would have di dj tensor dk. And so on and so on. But so even if now it's more complicated, the structure of these two products is sort of the same. So they are the exponentiation of this bidifferential operator. And notice also that this only depends in the end by the structure constants of the Poisson bracket. So here it only depends on the structure constant of the Lie bracket. While here it only depends on the structure constant of the symplectic form. So these will be the two characteristics that we want to keep in mind from these two products. Now, there is a general way to write down formulae to produce star products for graded Poisson algebras, which uses this concept of quantization loops. So first of all, we need to find an algebra A that's a quantization for our Poisson algebra P. So such that, so a filtered algebra such that is associated graded is isomorphic to P. Then we can take what we call a quantization map. Which is a map that is isomorphic to the level of vector spaces. And we also want it to be the inverse of this, so of this projection to the point. So if we start from something in degree n here, the Poisson algebra, we use phi, and we map into a term an element in the nth term of the filtration. Then we can use this projection to the quotient, and we go back into Pn. We want this composition to be equal to the identity. Once we have this true property, we can write this start product simply as the pullback of the associative product through this map. So we take A, we take B, we map them to the associative algebra with phi, we compute the product there, whatever it is, and then we pull it back with phi. This will give an associative product, and particular P with this product here will now be isomorphic to A. So this is a way to produce a graded star product. It's actually, if one restricts to only to this star product of this form, so ignores all the formal things that one can obtain, this is actually every star product will be obtained in this way, but with a certain quantization map. Why? Because one, again, could just simply consider as the quantization the algebra P with the star product itself. That gives an associative algebra. Then one can take the identity map as quantization map. So this is actually all star products are obtained this way. But of course, this is a very implicit way of defining the product. It's not very useful for computations. So it's what one actually wants is an explicit formula like the one we had before. But for the sake, so in the case of the Moyal-Weil, one can obtain using a quantization map by considering the Weil algebra. So the Weil algebra associated to the symplectic vector space, its associated graded will be the symmetric algebra on the vector space. And one can take as quantization map the symmetrization map. So one takes one of these monomial and just send it into, well, here all the order are the same. So while here in the associative, in the non-commutative side, the order matters. So we don't want to discriminate. We just do the average over all the possible orderings of this monomial. And for the good star product, we do, so one can show that this produces a Moyal-Weil star product. For the good star product, it's very similar. Here the quantization, the quantum algebra will be the universal enveloping algebra of Arlie algebra. Again, it's well known. It's associated graded is symmetric algebra. And we can take as quantization map the same symmetrization map as before. Now, of course, this on the basis, these would be elements of G. Okay. So this is a sort of idea for the classical side. And this once one have this two sides, so one says, well, this product has this explicit formula, but also creates we also show that this creates an algebra that is isomorphic to an associative algebra that we know of. This is, gives it's more useful. It's because now we can, if we care about now the Weil algebra or the universal enveloping algebra, we can do operations about them inside the Poisson algebra using only operations of the Poisson algebra, which are easier to control and compute. So this gives us also new insight on the associative algebra that we care about. So this can be a very useful tool. Now the idea is to do something similar, as I said, in the chiral level. So yeah, first of all, just a little remark that these two examples can actually be thought sort of the same big example if we think of the symplectic vector space as a sort of a non-linearly algebra where the Lie bracket is just a scalar and it's just given by the symplectic form. Then the Weil algebra can be thought of its universal enveloping algebra. So we can say that our framework is as following. We start with a non-linear Lie algebra G, then we consider its universal enveloping algebra, its symmetric algebra, and as quantization map, this symmetrization map. Now we want to chiralize this. So what do we get? Well, the Lie algebra will be substituted now by a Lie conformal algebra. Again, possibly with scalar lambda bracket. So again, so here the Lie bracket will be substituted by a lambda bracket. And we also get this sort of derivation T. Its universal enveloping algebra is this, called universal enveloping vertex algebra. Is a vertex algebra that can be thought as an associative algebra with this normally ordered product, this derivation T, again the lambda bracket. We can think as this the same way as we think of the universal enveloping algebra as the sort of free algebra that we can sort of construct from the Lie algebra such that the Lie bracket becomes the commutator. This one is the free algebra that we can construct from the Lie conformal algebra, generated from the Lie conformal algebra such that the lambda bracket becomes the lambda bracket of the vertex algebra. And so will be related to the, now it's not the commutator of the normally ordered product, but it's still related to the normally ordered product because the commutator and the associator of the normally ordered product are written in terms of the lambda bracket. And if we take the symmetric algebra of this Lie conformal algebra, we get a Poisson vertex algebra. So this will be a commutative differential algebra. So usually, I mean, this del will be, the differential will be T, but usually in this, it's common here to just call it, use the notation del. And then our Poisson lambda bracket, which again, all these lambda.
One
Yes,
question. What do you mean with nonlinear Lie algebra? If you don't mind
so
more about that? A
so
nonlinear Lie
nonlinear,
conformal algebra.
yeah.
Thank you.
So in general, I guess it's more complicated. What I mean here is just that I admit Lie brackets or that are scalar. So for example, the symplectic vector space V omega. This is not a Lie algebra, of course, because omega gives scalar, goes into C. But if we ignore this fact and we see, well, omega surely is antisymmetric and it trivially satisfies the Jacobi identity because, of course, it's easier to satisfy. It's always satisfied when with scalar terms. And so we can think of it as being sort of this non-linear Lie algebra. It's just to unify the two examples into one single framework, because then everything sort of works the same way, mainly because the main tool that we use to make everything works was the fact that this algebra was PBW generated by G, and the same way the Weil algebra is PBW generated by the vector space B. So this is the thing that we actually need. So by a non-linearly conformal algebra, for example, I can admit something like beta gamma system. So something where this Lie bracket, where this lambda bracket is scalar, something like this. Again, this is technically not a Lie conformal algebra, but we can put it in the same framework. Otherwise, one can think of a non-linearly conformal algebra as a quotient of a Lie conformal algebra by putting a central element equal to a constant.
Thank you.
Yeah, you're welcome. Thank you for the question. Okay, so this is sort of the framework that we will move to. And yeah, so by chiralization, I mean, we mean that there is a way to relate these two, the level above and the level before, and this is by this Ju functor. So sort of connects the two levels. Now, the idea here is to just imitate what we were doing before. So here we had this quantization map phi, which was just a symmetrization map. And again, this worked. This was a quantization map because of the PBW basis. Now the thing is that again here we have the PBW basis with respect to now this normally ordered product. So our new phi, we guess it to be a map that will say a monomial like this now in SR monomial here now instead of doing the associative product, we do this non-associative normally ordered product. And here, when I don't write parentheses, since this is non-associative, the convention is this is associated to the right. So unless I write parentheses, this is always written in this normal form like this. No, okay. Let's see some examples of this. The new framework for the example we discussed before. So in the case of the Lie algebra, get this diagram here. This one is here is the affine vertex algebra. So there's this lambda bracket here when A and B are element of G. And the Poisson vertex algebra here is an algebra of differential polynomial. So you can think of it as the polynomial algebra generated by the elements of G and all their formal derivatives. Again, here we use the symbol del, actually mean T in the vertex algebra. Okay. And for the symplectic vector space, the Weil algebra, the Chiralization is, as spoiled before, is a beta gamma system. So in the case with dimension of V equal to 2, it's the algebra free generated, for example, by this xy with this relation here, this lambda bracket here. And again, here, the Poisson vertex algebra is an algebra of differential polynomial. So, okay. Now we have the same framework. We have written down what we quantization map. So we want to proceed as before. So before we were pulling back the associative product, which is the only structure of the associative algebra. Now for the vertex algebra, if we want to do the same, we know that the normally ordered product is not enough to write down the whole structure of the vertex algebra. So one would need to pull back all the infinite n products, so all the vertex operators, for example. And so we'll get something that we call the star deformation. So it's, again, the pullback of the vertex operator of the vertex algebra inside the Poisson vertex algebra through this quantization map, which is the symmetrization. Now, the thing is that, again, one would like an explicit formula, and to get the explicit formula, one needs to compute it. And so one would like to do the least computation as possible. So we know that actually the whole vertex operator is a bit redundant. So we actually only care about the -1 product and the non-negative products. And then we can obtain all the other negative products using T. And really, we know that we can conveniently pack together all the non-negative products inside this lambda bracket formalism. So one can equivalently, and with less computation, just compute these two pullbacks, and that will be enough. So we'll get an actual star product with the pullback of the normally ordered product, and a star lambda bracket, which will be the pullback of the lambda bracket. Again, one can doing this computation, one would realize that it's actually doing sort of the same thing twice. And in fact, the thing that's more convenient to pull back is maybe it's a more or less well-known formally for the vertex algebra. This is called the integral lambda bracket. So one can pack together the normally ordered product and the lambda bracket, or better, its integral, into a single operator, which is called integral lambda bracket. And well, one doesn't lose anything by doing this, because one can always go back. Putting lambda equals 0, we just obtain the product, and doing derivative, one gets the lambda bracket. So we don't lose anything, and actually, I mean, it's just more practical to do the computation here, because one realizes that otherwise it's doing the same thing more or less twice. And then once one computes so for us, star deformation will be a formula, an explicit formula for this pullback of the integral lambda bracket. Then if one cares about the other two things, can easily obtain them using this formula here. Okay. Now, what's the idea to do this computation? Well, when for the Poisson case, we have this two symmetrized polynomial. So if we want to compute the star product of two polynomials P and Q, we need to do the symmetrization, then multiply them together inside the associative algebra. Now, this product won't be a symmetrized polynomial anymore, but so one needs to use the commutation relation in the associative algebra to rewrite this as maybe a sum of symmetrized figs, which then can pull back directly. So it's just a question of computing all this reordering and taking track of all the extra terms that one obtained by using the commutation relation, and then it's sort of a recursive thing that at some point likely ends because of degree reasons. Now, in our case, there's also another problem that if we have something that is a product with the normalized order of parentheses, and we multiply two of them together, the product won't have now the parentheses in the correct order because this algebra is non-associative. So we also need to fix the associator. So there are these two things to do. So commutativity and associativity. Now, the idea is to try and do the two things separately. So instead of going directly from the Poisson vertex algebra to the vertex algebra, we take this stop in between. So what is this algebra here? So this is actually a universal enveloping algebra. So an associative algebra, an actual universal enveloping algebra of a honest Lie algebra, that's this R Lie. So as a vector space is still R. And we just write on it this Lie bracket that makes it a Lie algebra. So this one is it would be the commutator of the normally ordered product in terms of lambda bracket is written like this. So it's a commutator, so it gives a Lie bracket. So our Lie can be made a Lie algebra like this, and then we can consider its universal enveloping algebra. And gamma will be defined as inductively as gamma of A equal to A for R for A in R, and gamma of AB equal to A for my order product with gamma dB. For generic B. So basically, this is imposing the order of parentheses that we discussed about as the normal one. So associating on the right first. So we split the problem into two. We have this bit here, gamma, and pulling back along this one imposes us to fit all the parentheses. And this pullback then psi, which is now just an ordinary quantization map of the type we were discussing before between Poisson algebras and associative algebras. So if we have our integral lambda bracket here, and here it will give us the star lambda bracket, we can sort of consider a thing in between. We could call it a lambda cap with this cap, which will be the pullback along gamma of this integral lambda bracket. So this first step in which we fit the associators. Now what's what happens? The sort of, so we can write this I lambda star as just a pullback along psi of this I lambda cap. Now, let's hope that this thing, we get a formula. First, we need to compute a formula for this thing. And let's assume that once we compute it, we find out that we can actually write it as the product of two symmetrized things. Then what we are computing is the pullback by psi of the product of two symmetrized things, which by definition of what we were doing before, this is just the ordinary star product between the two. In this case, this is actually just the good star product, or the Moyal-Weil in the scalar case. Because we see this is a symmetric algebra and universal enveloping algebra for the algebra. So one can just needs to hope that this thing is true, but luckily it is. So this thing actually, this splitting it into two parts actually works and make it tractable to compute. So show you now the formula that you get in the two different cases. So first, the easiest one, the free field one, which particularly includes the beta gamma system. So you can sort of think of it as sort of related to the Moyal-Weil product. So in this case, well, as you could expect, things are easier. In particular, we get that this Lie algebra R Lie is abelian. Why? Because the bracket is like this. Now, free field means that this thing is just a scalar, or polynomial in lambda with scalar coefficients. And when we compute this formal integral, we apply these t's that kill all the scalars. So this is 0. So these first two things are actually the same. Psi will be the identity, so we don't have one of the two steps. So we just need to compute that I cap, basically. And the formula looks like this. So sort of can see the similarity with the Moyal-Weil one. We have again this exponentiation of this term here. Now, this thing is like this. Now, it's not quite in this form explicitly a bidifferential operator, but it's just one in disguise. So the thing is that the Poisson lambda bracket has Leibniz rule on the second one. So morally, we are exponentiating this sort of integral of the Poisson lambda bracket. Then we can apply Leibniz rule on the second term to take out, and we get a differential operator. Leibniz rule on the first term is more sort of it's a deformed Leibniz rule. We can still use it to get an explicit bidifferential operator, like done like this. So we see that what we're doing to A and B is actually just derivatives. And now, and again, the coefficients are multiplied by an expression that only depends on the structure constant of the Poisson lambda bracket. So we still get the two things we had before. So this sort of bidifferential operator. And the structure only depends on structure constants. But this is nice. And so it's not even, it's not, something we like. And yeah, that's some striking similarity with the Moyal-Weil star product. Again, this is if one just wants the actual products, one just puts lambda equal to 0 in all this formula. And if one wants the lambda bracket, one would keep lambda and puts a derivative. But you see now that it's actually, what controls everything are these operators here. And then depending on what we put into lambda, we get the difference part of the vertex algebra structure. So that's why it's more natural to actually compute it, use this weird integral lambda bracket to compute everything. Now, the linear case, which would correspond to the good star product, is more complicated, as you can see. But we can still appreciate something. So first of all, we still have our sort of bidifferential structure, bidifferential operator. Now, it's quite complicated, but that's still sort of how it works. And again, ultimately, all these the coefficients, even if in a very complicated way, ultimately only depends again on the structure constants. So we have these two caveats that we keep from the Poisson case. Now this is actually good. So in the Poisson case, there are some results. For example, there's this famous result by Kontsevich that basically says that, under some assumption, all the even formal quantization of certain Poisson algebra are in fact completely determined by the Poisson structure, by the Poisson bracket itself. So these, of course, are only the two easiest possible case of this star deformation of Poisson vertex algebra, but it's nice to see that at least here we re-obtained what we had in the Poisson case. Also, I should say here, so we said so now, of course, now we won't have anymore this fact that the algebra is abelian, but that in fact, is not the main complication. In fact, that only influences this bit here. So now these things are actually good star products. So as I was saying, we have to do this thing in 2 steps, and we end up with what we will end up with are some good star products between some weird formula that we obtain starting from A and B. This is exactly what happened. So we have this weird complicated expression from A and B, and then we need to compute the good star product between them. But that's just a problem in that classical comes from the Poisson, the star product for classical Poisson algebras. Okay. Now, there are any questions about this? Okay. So otherwise, then go to the next part of the talk, which will be about compatibility with the G functor. So we talked about how we have this this was the sort of diagrams that we had, and now we have this natural question. So if we do we get back our original formula after applying ZOO? Now, one would hope so, like that we did basically the same thing. We used the same sort of quantization map. The fact is no, and no in a very bad way. So the fact is that these formula that we get are actually you can't even like send them down. They will not even be well defined. So to explain that, I'll say something. So I'll recall some things about this G functor. So this is essentially a quotient. So to a vertex algebra V associates this new algebra that as a vector space is this quotient. So one has to define these new shoe products, circle and asterisk. Fortunately, and well, one finds out that this space here is actually an ideal with respect to this new asterisk product. And so this thing is actually a well-defined algebra that miraculously becomes an associative algebra. This is how Zhu defined this Zhu algebra, which is a very important role in the representation theory of vertex algebras, and sort of, again, bridges between the two worlds. Now, the thing, this is the key, the fact that the product here is this asterisk product, which is a deformation of the normally ordered product, but it's not normally ordered product. So since all our constructions were done using the normally ordered, starting from the normally ordered product, pulling back the normally ordered product, this thing won't go down. It's not defined in the quotient. We can see this is like in an example. So for example, in a beta gamma system, the commutator between x and y with respect to the normally ordered product, if you use the formula, as we said before, this thing, this Lie algebra here is abelian, so this thing is 0. Again, for the same reason, this is a scalar. Well, it's actually 1. So if this was in any way the product related on the zoo algebra, we'll get a commutative algebra. But while we know we get the Weil algebra, so that's not what we want to do. While if one uses this asterisk product, instead gets back 1 than what one would expect. So what's the idea? So first of all, how are these things defined? So there are, well, that I know of, 2 construction. One is the original one by Zhu, and the other one is this one here is actually due to Huang. But again, uses some ideas that were in the original Zhu paper. So one defines this deformed, one can define these deformed vertex operators in this sort of weird way. And one obtained this by collecting the z's, one obtained these deformed end products. Now, the 4 minus 1 product gives the asterisk product, and the 4 minus 2 gives the circle product. Now, luckily, well, one can show that the order monomials with respect to asterisk still give a PBW basis in our examples. So, okay, that's good. So we can do the same thing again, and now send everything into these symmetrized things. Now one can show that sort of an implicit, it's not too hard to show by basically showing that this map phi sends the kernel of one projection into the kernel of the other. So this will be pz is qz, and this phi sends the kernel of one into the kernel of the other, and so one can show that now it actually works. So the star product defined by this. So here I mean the pullback with this new phi of the asterisk product, and here I mean the pullback with the induced map to the quotient. And these 2 things are the same. Now works well with the quotient. So if I compute this thing and then I do the zoo quotient, I get back the formula for the original star product. Now the question is, how do I compute an explicit formula for this thing? Because now I don't have, like, these products here are a bit like we can write them explicit, like there is a formula for them, but they are deformation of the normally ordered product, which was already very complicated. And in fact, the good thing about writing this quantization, this explicit formula here, is that one has now an explicit way of computing this normally ordered product and lambda bracket by using a structure of the Poisson vertex algebra, which is easier. And even there, we see that the formulae are very complicated. And this product here is even a deformation of that, so it should be even more complicated. Well, if one goes back, the idea is that everything works, everything is manageable because we have the lambda bracket. So we would want something similar for this deformed thing here. Now, this is sort of the idea. One can take this deformed vertex operators, which I recall are something that looks like this. And let's say that let's call these hats. So we can think of this as sort of the original vertex operator under a formal change of variable, and then we expand in the new variables. That's sort of what we're doing. Now, since this is a nice change of variables, one can, quite easily, it turns out that these satisfy the vacuum axiom and the locality axiom, this new deformed vertex operator. And the only one that they don't satisfy of the axioms of a vertex algebra is the translation covariance. But one can show that by chain rule that they satisfy this sort of deformed translation covariance. So in which now this commutator with t does not give just the derivative in z, but we need multiplied by this step in front. And well, the thing is that these still look a lot similar, like they're still very similar to we have not deformed the axioms of vertex algebra too much. They're still very much the same. And one can go through basically the first chapters of a book on the structural theory of vertex algebras and reprove all the sort of analogs of all the lemmas there until one arrive to the definition of the lambda bracket. So what I get is this new bracket here, this deformed lambda bracket. So it packs together all the non-negative deformed products and just packs them in a weird way. So this is the main difference that turns out. So instead of using lambda to the n, we use this falling factorial. Otherwise, it doesn't work. So this is what the fully factorial is, and this is a discretization of the power of lambda to the n. And so, in fact, the only thing that really changes is that we saw a lot of, there are a lot of formulae, and we saw a lot of them formulae for vertex algebras where we appear integrals, formal integrals or formal derivatives appear. So integrals in lambda and stuff like that. What changes is that all these formulae here, we need to go from sort of formal calculus to formal discrete calculus. So in fact, we can show that sample of the new formula for the commutator. So the commutator of this ast product can actually be written in terms of this lambda h deformed bracket, only that we don't do the integral, we do this sigma here, and this is the sort of discrete integral. Apparently, it's called definite sum also. And this is just the inverse of the finite difference operator. So the derivative before sending the limit of h to 0. But for the rest, everything works more or less the same. And in fact, one can write, so this, I wrote it here, is the formula in the free field case. One can see that this, it looks almost the same. The only things that, it looks the same because I didn't change this L here. Now this L, you will need to write instead of like this, with the integral and the lambda bracket, you will put a definite sum and the deformed lambda bracket. But for the rest, the formula looks exactly the same. The only other difference is this m here. This is now not m the standard multiplication as we had before. It's actually, this is the Moyal-Weil product. Why? Because again, remember the idea of splitting the thing into two, and from this term, from this part here, I would get these ordinary star products. The free field case before for vertex algebra, we don't get them because we have this R'Lee is abelian. While here, R'Lee is no longer abelian, but that was exactly the thing. So we don't want this. We don't want the ZU algebra to be commutative, and so we don't want this product, this AST product, to be commutative between free fields. And the new formula saves us in corner because it's the same. Again, this is just a scalar, and so this T will kill it. But there is this miraculous minus h bar here that if you put h bar to 0, which is go back to the vertex algebra, it gives 0, but here, no. So one needs to consider both the two steps, so fixing the associators and fixing the commutators. So here we get still the star product like we had it in the non-free field case. And then this sigma here again appear mysteriously. This is just sending X tensor Y in Y tensor X. And one can show that this now in the quotient goes back to the Moyal-Weil product. I mean, we showed it. One can show it implicitly with the proof before, but here it's easy to see it explicitly. The only thing the only thing that's not clear is that this thing in the quotient is just omega, the Poisson bivector. But apart from that, then this becomes the Moyal-Weil product sigma plus exponential of omega. Then the star product itself was M composed with S of omega half. This was the Moyal-Weil product. We move this sigma around. So this is M sigma. Omega is symplectic form, so here it changes signs. And now this M is the multiplication in the Poisson algebra, so it's commutative, so this sigma disappears. So this is just M composed with exp of omega half, which was exactly the formula we started with for the Moyal-Weil star product. So in this case, it's actually quite easy to see that it goes back in the quotient to what we want. So in the end, we have these two things that we can consider in the vertex algebra case. We can consider the deformation of the Poisson vertex algebra into a vertex algebra, which is useful for its ways. Also to consider the structure of the vertex algebra in an easier setting. But if we want to care with the actual chiralization of the star product, so a formula that when we apply the ZU functor goes back to the original formula of the star product, what one has to consider is actually this weird deformed thing here. Okay, and that's what I wanted to say for today. Thank you for listening.
Thank you very much, Simone. Let me stop the recording so we can move on to questions.